Okay, so this will be the second lecture out of chapter 22. So in this lecture, we're going to cover several different reactions that students sometimes struggle with. First one we're going to cover is what's called the Aldol reaction. So if you take an aldehyde or a ketone and react it with a base and nothing else, so you don't give it anything else to react with, then what will happen is it will react with itself. So let's not do that. So let's take this and copy it and paste it. So basically what's going to happen is we're going to end up making a bond between the alpha carbon of one, so two aldehydes are going to react with each other. So we're going to end up making a bond between the alpha carbon of one and the carbon oxygen double bond of the other, and then that's going to become an OH. So that would give you this product, right? And that's what's called the Aldol product. Why is it called an Aldol product? Well, you have an aldehyde, so that's where that comes from, and you have an alcohol, which is where that comes from. So this is an important reaction in organic chemistry, right? Why is it an important reaction in organic chemistry? Because you make a carbon-carbon bond, and anytime again you can make carbon-carbon bonds, you can take simple molecules and make more complex molecules from them. So that's an important reaction in organic chemistry. So you could stop it here with the alcohol aldehyde, the aldol product, but if you heat this reaction up, then it can undergo another step. It can undergo a dehydration where you can lose H and OH, and so you can lose a water molecule and then put a double bond in between them. So that would be put on the double bond here. So you make them what's called an alpha beta unsaturated aldehyde in this case. So the significance being, why does that want to happen? Because you make conjugated double bonds, and that's very stabilizing. So the aldol product naturally wants to lose water to make the alkene so that it's conjugated with the C double bond O. So if you're not careful with aldol products, if you heat them too much, then they will undergo dehydration, sometimes spontaneously. If it leads to a very highly conjugated system, you probably can't even stop it at the aldol product. It will just dehydrate on its own without heat. Okay, so how does this reaction occur? So let's go through the mechanism. So I've sketched out one of the alpha hydrogens, since we're going to need to lose that hydrogen. So if we react this with the base, so hydroxide can take that hydrogen, those electrons become a lone pair on the alpha carbon. That's not a bad place to put the lone pair, right, because it's resonance stabilized. So if you don't give so in the last lecture, we gave it something to react with. We reacted it with an alkyl halide, for example, so it could do an SN2 reaction. But if you don't give it anything to react with, then it will react with another molecule of itself. So we're going to take that lone pair and we're going to make a bond. So that carbon's partial positive, of course, so this carbon's negative, and it's going to be attracted to the partial positive carbon. So we'll take the lone pair, make a bond of that carbon, and then break the double bond, because you can't put 5 bonds on carbon. So that gives us this, and then that oxygen that's negative will react with the water molecule, pull a hydrogen off. So you'll remake hydroxide. And now you have the aldol product, right? Because you have the alcohol and you have the aldehyde. So that's the aldol stage. And if you didn't use heat, you might be able to stop it at that point and isolate that product. If you heated this up, then this can dehydrate. So how does it dehydrate? So another equivalent of base comes in, takes another alpha hydrogen, but this time these electrons can go here to make a carbon-carbon double bond, and it can kick off hydroxide. So you're basically losing a water molecule, right? You're losing a hydrogen here, and you're losing OH there, and you're making a double bond between them. So you want to put the double bond there so that it's conjugated with the C double bond O. Right? You could conceivably put the double bond here, but you don't, by losing a hydrogen from here. But you don't want to do that, because if you put the double bond there, so we'll call this 1 and we'll call that 2. If you put the double bond between those two carbons at 2, the double bond would not be conjugated with the C double bond O. So it would rather be at position 1 so that it's conjugated with C double bond O. And then that gives you this product, the alpha beta unsaturated aldehyde. Okay, so let's take another example. So how to see these products. So we have an aldehyde, could be a ketone, and you react it with a base and nothing else. Then you're going to be doing an aldol reaction. So the easiest way to see these products is to take two of the aldehydes like I've done here and sketch them again and line the alpha carbon up with the C double bond O of another carbon. So then you're basically going to make a bond. So we're going to lose a hydrogen because the base is going to take one of those hydrogens off. And you're going to make a bond here. And then this is going to become an OH, right? And that's your aldol product. And then if you dehydrate that, then you're simply going to lose OH and H. So you're going to lose a hydrogen between the C double bond O and the OH so that the double bond ends up conjugated. So then you're going to put the double bond between those two atoms. So we're going to lose this, and we're going to lose two hydrogens, and we're going to put a double bond there. And that would be your product. So we can just take that, copy it, paste it. We're going to get rid of this. Going to get rid of that. Those two hydrogens. Put a double bond there. And that's your product. That's your alpha beta unsaturated aldehyde. Okay, so this will be the Aldol stage. And this would be if dehydrates. Which in this case, it would be difficult for it to not dehydrate because now it's conjugated not only with the C double bond O, but it's also conjugated with a benzene ring, so that's an even more stable carbon-oxygen, carbon-carbon double bond. So this would be more easy to dehydrate than this would be, for example, where it's only conjugated with the C double bond O. Okay, so this is where it gets more difficult. So you can start doing intramolecular versions of these. So here we have two. So here we had two aldehydes. Here we had two aldehydes that reacted with each other. Here we have two aldehydes. They just happen to be in the same molecule, which means they're going to make a ring in the process. So if we react this with a base, so you can make an enolate there, or you can make an enolate there. Doesn't matter because of the molecules symmetric that I chose to use. So if we use the base to make an enolate, so take a hydrogen from the alpha carbon, those electrons go there to make a lone pair. And now that carbon's partial positive and that's negative, so this is going to want to react here and then break the C double bond L. So that's going to close into a ring. So again, let's number 1, 2, 3, 4, 5. So that'll make a 6-membered ring. So draw a 6-membered ring. Right, arbitrarily number it. And now get everything in the right spot. So carbon number 1 has that aldehyde attached. 2 is a CH2. 3 has 2 methyl groups. 4 and 5 are CH2s. 6 now is an O minus. That used to be a C double bond O. And then that's going to pick up a hydrogen. And that would be your aldol product. Right? So now, since you're heating, so now we're going to dehydrate this. So if you dehydrate this, so where's the double bond going to go? Well, it's going to go between those two carbons, right? Always has to go between the C double bond O and the carbon that has the OH on it so that you end up with conjugated double bond. So what's going to happen is, right, this hydrogen is going to come off. So hydroxide takes that hydrogen, those electrons go there to make a double bond, and hydroxide comes off. Right, and that would be your dehydration product. Okay, you can do crossed aldols. So if we take two different aldehydes, they can react with each other. So how many places can you make an enolate between these two molecules? Only one, right? That's the only alpha carbon that has hydrogens on it. This alpha carbon does not have hydrogen, so you can't make an enolate there. So the only enolate that you can make is on that position. And so now then if that reacts here and that becomes an OH, then you would make right, that will be your aldol product, and then if that dehydrates, you would make that as your product. So that's but there is another possible product here, right? Because two of these aldehydes, those two could react with each other. So you could have also made that aldol product. So that could have reacted here, or that could have reacted there to make that C double bond O and OH. And then if that dehydrates, you could have made that as a second possible product. So if you wanted to only make one, if you only wanted to make this one, how could you favor that reaction? Well, you could just use more benzaldehyde, right? So if you have an excess of benzaldehyde, it can't do anything besides react with the enolate. So if you have a whole bunch of this, then chances are that this enolate that you make would find benzaldehyde before it found the other aldehyde. And so that would give you more of this product and less of this product, right? But there's two possible aldol products that you could make. Okay, so what if you did this crossed aldol? How many different aldol products can you make? Well, so how many different places can you make an enolate? You can make an enolate there, or you can make an enolate there, or you can make an enolate there, right? At all of the alpha positions that have hydrogens. So you can make that enolate. Or you could have took a hydrogen from the CH3, and you can make that enolate, or you could have made that enolate. So three different enolates, and then what can each one react with? Well, this could react with itself. Or this could react with the other aldehyde. So that's going to be two possible aldol products. This could react with itself. Or it could react with the other aldehyde. And the same is true for this. It could react with itself, or it could react with the other ketone in this case. So that's going to lead to 6 possible products, right? So let's see if I can sketch them right quick. So that could react with itself. Let's do it this way. So I'll just sketch 2, and then so that you can see the concept. So if I draw these 2, I'm missing a carbon. Okay, so I drew those 2 molecules again, so now I'm going to attach this to here, and that's going to become an OH. So get rid of that, get rid of that, so we'll make a bond here. Right, so that would be one possible aldol product. Or this could attack here, and that goes there. And that would be a second possible aldol product. And then you would do the same thing here. You would let the middle enolate react with itself or the other aldehyde, and make the right enolate react with itself or the ketone. So you get 6 possible aldol products, and then potential dehydration to get dehydration products as well. So obviously that would not be a very good synthesis because there's too many aldol products. It's just to illustrate the concept to see if you can see all of the possible aldol products or not. So there'll be a question like that on the 202 tutorial class. Okay, so there's an ester version of this. The ester version of this, rather than aldehydes and ketones, if you used esters instead, then that's what's known as a Claisen condensation. So if you take an ester with a base and then don't give it anything else to react with, then it will react with itself. So here's the mechanism. So you would typically use the conjugate base, so whatever the alcohol is, so you would typically use the conjugate base of that alcohol, because if this reacted here and kicked that off, if you had a different conjugate base of an alcohol, you would do a transesterification, and we don't want to do that. So if this OCH3 attacks the carbon-oxygen double bond and kicks off OCH3, then you get the same thing back. So that doesn't matter if that happens. So we used OCH3 since we have the OCH3 ester, so that acts as a base, takes off a hydrogen at the alpha position. Now you have an enolate, and the enolate's going to react at the C double bond O since that's partial positive. So we'll attack here. So this is just like the aldol, and then break the C double bond O. And now we have this, and this is where it's different than the aldol, because if this was the aldol, then what we would do at this point is we would pick up a hydrogen on that oxygen and make that an OH, right? But that's not what we're going to do here. So what we're going to do instead is we're not going to make this an OH, we're going to remake the carbon-oxygen double bond, and we're going to kick off the leaving group OCH3. All right, so now you have a beta keto ester. And so you could stop it at that point. So if we didn't do step 2, if we didn't do H2OH plus and water, then you would stop at the beta keto ester. But if we do H2OH plus, then that's going to hydrolyze the ester, right, to a carboxylic acid. And now you have a beta keto acid, right? So alpha beta, and if you remember, those are not stable. If you heat those, then they can decarboxylate. So now we're going to lose CO2, and if you bump the hydrogen down into its place, then now you have a ketone. And of course, that would be the same thing as this. Okay, so for the Claisen condensation, then you end up with a ketone as the product. or a beta keto ester if you don't do the hydrolysis and decarboxylation step. All right, so how do you see the products? So you could see them just by working through the whole mechanism, or the easier way. So let's line up the alpha position of one with the C double bond O of the other, right? So you're going to make an enolate at the alpha position, and then that's going to attach here, and you're going to kick that off. Right, so through this mechanism. But that's just a way to think about how to see the product. So alpha position on one attacks carbon oxygen double bond on the other and kicks off the OR group. So now you have the beta keto ester, and if you do H2OH plus, then that's going to knock this off, and you have a carboxylic acid. So if we just take this whole thing, copy and paste it, and then now that's gone, and you have the carboxylic acid instead. And then if you heat that up, so again, if we just copy this, paste it here, let's move this out of the way first. Then that just loses all of this, right? CO2 goes away, and that's your product. Okay, so you can do, just like with the aldol, you can do an intramolecular version of this. So an intramolecular Claisen condensation is what's known as a Diekmann cyclization. So if we take this molecule, react it with the KOET, so OET, so that's your base. So you can make an enolate here and here. Again, because I chose a symmetrical ester, it doesn't matter which one. If it was non-symmetrical, then there would be two possible products. But since it's symmetrical, then it doesn't matter which one you make the enolate on. So we'll just lose a hydrogen from here. Those electrons go there. So now you have an enolate, and if you don't give it anything to react with, it reacts with itself. So this is going to attack here and break that, right? So now you're going to make a 1, 2, 3, 4, 5, 6 member ring. So we'll call that 1, 2, 3, 4, 5, 6. So one has the ester on it, and it has a methyl group on it. 2, 3, and 4 are CH2s. 5 has a methyl, and 6 has the O minus and the OET on it. Okay, so now what we do is we remake the double bond and kick off the OET group, right? So now 6 has a C double bond O on it. And then if we do the H2OH plus, that's going to hydrolyze the ester and convert that to a carboxylic acid. And then if you heat that up, then you're going to lose CO2 and bump hydrogen down into its place. And that would be your final product. So hopefully you would agree that this is a little bit harder to see the products than previous reactions that we've done in organic chemistry 1 and 2. So this is why this is a much harder chapter, I think, for most students, because to see the product, you kind of have to think about all of the steps along the pathway. So just like with the aldol, you can do crossed aldol, you can do cross Claisen as well. So if you have two different esters, then they can react with each other. So how many places can you make an enolate? That's the only one that's that's the only alpha carbon that has a hydrogen. So the only enolate that you can make is at that position, right? And then that enolate would have two choices. It could either react with itself, or it could react with this ester. So if we call that A and B, so if you wanted to react to pathway B, then you would just use a lot of this methyl benzoate. So that once you made the enolate, if there was a whole bunch of methyl benzoate in there, then the chances are that enolate would follow pathway B instead. But there are two possible Claisen condensation products. Okay, so if we just take pathway B, then this goes there. So that has an ethyl and a methyl on that carbon. And then remake the C double bond O, kick off that. And then hydrolyze and decarboxylate. And that would be your product. All right, so basically what we did is we just took all of that and stuck it on this carbon, right? Because all of this ends up going away through hydrolysis and decarboxylation. And then of course we got rid of the OCH3 as well in the course of this mechanism. Okay, so lastly, so you could do a cross between an ester and a ketone or aldehyde. So in this case, how many acidic positions are there? Well, that's acidic, that's acidic, that's acidic, right? But this is the same. Those two are the same because of the symmetry. So we'll say A and B. So two possible enolates that you could make. So which is more acidic, ketones or esters? So you can see the pKa's here. So that's got a lower pKa, so ketones are more acidic than esters. So if we react it with a base, this is going to be the enolate that you make. So why are ketones more acidic than esters? So if we take a hydrogen off of here and make this conjugate base, the enolate, well, this is resonance stabilized through that oxygen, right? And same for the ester. If you lose one of these hydrogens, those electrons go here to make an enolate, and that's resonance stabilized through the C double bond O. Right? The problem is that the carbon-oxygen double bond is already tied up in resonance, because you could take the lone pair on oxygen and move those down to make a double bond. Let's just do this in a different color. Right, you could do this instead. You could take those, move these down and make a double bond there, and move these up and draw this resonance form. So the significance is that the C double bond O is less available to stabilize that negative because the carbon-oxygen double bond is already tied up in resonance with oxygen. And so the carbon-oxygen double bond is less available to help stabilize the enolate. So therefore it's less stable when it's harder to make. So the ketone is more acidic than the ester, right? Okay, so then if you did this reaction, if you took the ketone and the ester and reacted it with a base, then the point is you're going to make the enolate on the ketone and not the ester. So now this enolate then will react with the ester. So take those electrons, break the C double bond O, and then remake the C double bond O and kick off the OET. And now you have a beta diketone and you're done. That's where it stops at. Okay, so let's take one more example. Okay, so if we do that reaction, 1, 2, 3, 4, 5. Then how many places can you make an enolate? So you can make an enolate here, here, or here, right? So we'll call that A, B, and C. So where would it be preferential to make an enolate would be A or B, because ketones are more acidic than esters, right? So A and B are alpha to a ketone, C double bond O. C is alpha to an ester, C double bond O, which is already tied up in resonance with the oxygen. So putting the negative on C is less favorable than putting it on A or B. So we could make two different enolates, A or B. So we could make that enolate, or we could make could have took a proton from here instead and made that enolate. Okay, so both are pretty about the same acidity, but one leads to a more favorable reaction than the other, because if you make this enolate, then where is it going to react at? It could react here, so that would make a 1, 2, 3, 4, 5 membered ring. Or if you made this enolate and it would react here, that would make a 1, 2, 3 membered ring, and obviously 5 membered rings are easier to make than 3 membered rings. So you would make both enolates. So you could put the proton on, take the proton off of here, but that's an equilibrium, and the proton could go back on to position B. And then if the proton comes off of A and you make this enolate, and then that reacts with carbon number 5 to do that Claisen-like reaction, then that's going to be the preferred pathway, because 5 membered rings are better than 3 membered rings. So we're going to make a 5 membered ring. So let's call this 1, 2, 3, 4, 5. So 1 has a benzene ring attached. 2 has a C double bond O. 3 is a CH2. 4 has a methyl group attached. 5 has the O minus now, and the OCH3. And then you would remake, right, the C double bond O, and you kick off the OCH3. And that would be your product. So that would be a beta diketone, right, just like this is a alpha beta diketone. Okay, we'll stop there.